Hello, my name is Rich Dionne. This is week 1 of the course in Prequalified Structures for Live Entertainment. Today we're going to talk about those terms, prequalified structures and pre-engineered construction techniques, define what they mean and why they matter for us in live entertainment. We're also going to talk about some other definitions, including forces, stresses, loads, and equilibrium. So let's get started. What do we mean by prequalified structures? Well, a prequalified structure or a pre-engineered structure is a construction that, when assembled according to previously defined best practices and/or instructions, can be assumed to support a specific load safely. What this means is that prior to assembly, these have been vetted and defined by engineers who determine the best materials for a desired purpose, the best structural shapes for that desired purpose, and the best orientation and assembly of those elements for the desired purpose. Why do we care about that in live entertainment? Well, one, we use them all the time. Think about aluminum trusses, think about orchestra shells, think about pre-manufactured decking panels, things manufactured by Wenger Corporation, by Steel Deck, by Stage Right, and other companies. These are all pre-qualified structures that have to be used exactly how they've been engineered to be used in order to be considered safe. And they've been created by structural engineers who provide guidance for how to use them safely. We also, all the time, use pre-qualified construction techniques, 2x4 framed platforms, stud walls or knee walls. Think about stress skin panels like Triscuits or Texas Triscuits. These techniques have been developed and vetted by engineers, and when followed as intended, they assure safety and strength for anything we can construct on stage. When pre-qualified structures are not used as intended, or when pre-engineered construction techniques are not followed correctly, structures may collapse. And more importantly, people can get hurt, people could be crushed or fall down, and finally, technicians and venues can become liable for any injuries or damages that occur from a failure of a structure. So in this course, we're going to explore the principles behind pre-engineered construction techniques. We're going to understand how and when to employ them. We're going to explore how to recognize if those techniques or structures haven't been employed safely. And we're going to learn how to understand and read manufacturers' guidelines for pre-qualified structures. In order to do that, we need to learn a number of definitions. So let's start right from the beginning. Load. What is a load? A load is any weight or force that is applied to a structure that causes members of that structure to undergo stress. So let's draw a picture. We'll consider a simple platform like this that is on 4 legs. Anytime there's a load on that platform, like a person, that's a load. I said that twice. Anytime there's something that causes a force to be applied is a load. Well, now wait a minute. What's a force? Hang on a second. A force is any push or pull on an object that could cause that object to change velocity. So consider many of you maybe have played pool, right? Consider the cue ball and the cue stick. You hit the cue stick into the cue ball, and that cue ball moves in a particular direction, right? So the cue stick imparts a force on the cue ball that causes it to move and change velocity. Loads impart forces. Forces are measured in terms of the magnitude of the force, the strength of that force in the US in pounds. Forces also act in a specific direction. In our cue ball and cue stick case, they are, in this case, moving left to right. An object that can move when acted upon by a force will usually move in the direction of that force. So the cue ball is going to move that direction when hit by a cue stick that hits it from this direction. Forces always act in straight lines, but some forces result in motion that is not straight. They cause rotation around an axis. We'll call these moments. So, classic example, a crescent wrench. And I'm going to do my best to draw a nut and a crescent wrench, but don't laugh at the illustration here. We've got a nut and we've got a crescent wrench, or we'll just call it a box wrench for today, so I don't have to get too complicated, just like that. I'm going to pull on the end of that wrench in this direction. I'm applying a force here in a straight line, but it causes rotation around this axis. That's a moment. Moments are measured in terms of force multiplied by the distance away from the axis of rotation where the force is acting. So if I push here with 14 pounds of force and this wrench is 6 inches long, I multiply the two together and I get 84 inch-pounds of force. Usually in the US, we measure moments in foot-pounds or inch-pounds. Okay, forces, loads, moments, fantastic. We're also going to talk about stresses in this course. What is a stress? A stress is the internal resistance that an object has to a force acting upon it. So objects acted on by forces respond in some way. Some move, either in a straight line or by rotating. Objects that cannot move resist the force applied, and they do so until they can no longer do so. So think about a nut that's rusted on. It stays there resisting the force applied and the moment that's happening until we break it free, or they break. Internally, these objects, when they are resisting the action of the force, are seeing internal stresses. So a stress, again, is an internal response to a force, usually measured in units of force per unit, in units of force per square unit of area. In the US, pounds per square foot or inches per square foot. There are two major kinds of stresses. Bear with me, this is going to get a little deep here for a minute. There are two major kinds of stresses. Axial stresses resist forces acting parallel to an axis of the structural element. Okay, there's a lot of words there. What does that mean? Consider a post. And we set a 100-pound block on top of that post. That post is seeing, and it's not moving because it's sitting on the earth, that post is seeing 100 pounds of force acting on it. It's not moving, so internally there are stresses that resist it. Here and here. They're pushing against the two things that are trying to squish it. That particular kind of axial stress is known as a compressive stress. It's trying to compress, the forces are trying to compress the element, and it's resisting that. We also might consider a chandelier hanging from a pipe. I'm not going to draw a pretty chandelier. We're just going to pretend it looks like this with a light bulb inside. The weight of the chandelier is pulling down. Internally, there are stresses acting to resist that movement and keep this pipe from stretching. And we'll call that a tensile axial stress. The other major kind of stress is a tangential stress, and there are two kinds of those as well that we'll talk about. The first is a shear stress. Shear stresses resist the tendency of one part of a body to slide past another part. Think about, we've got a board here and a board here, and this is attached to the ceiling somewhere, and this has another 100-pound weight on it. And right here, going through these boards, is a bolt. And at this joint, we see that that bolt kind of wants to slide across itself. That is a tangential stress, specifically a shear stress. And then finally, the last kind of tangential stress we'll talk about is a torsional stress. And that is a stress that resists twisting. So remember that example of the nut that didn't want to break loose because it was rusted? That bolt is trying to twist as we're trying to twist that nut. And so the bolt, which is not twisting, is resisting with a torsional stress. Okay. So we've got axial stresses, compressive or tensile, and tangential stresses, shear or torsional. We're also going to talk about some different kinds of loads in this class. We'll talk about static loads that refer to loads that don't change over time. And we'll talk about dynamic loads, and that refers to loads that do change over time. So think about, in a house, the floor and the walls and any permanent structures of the house all impart static loads because they don't change over time. But me, walking around my house, I do create a dynamic load because I'm not always there and where I am changes. In live entertainment, We use some substitution words for these. We talk about a dead load or a live load. In live entertainment, we're often dealing with temporary structures, things that aren't permanently up, right? A stage that comes in for a show, it might last for weeks, it might last for months, but eventually gets torn down. It's a temporary structure. And in that case, static and dynamic can't be easily used, right? A static load in a live entertainment situation is never going to be permanent, but we're going to have loads that don't change over time. So the dead load will typically refer to the weight of the structure itself, which never changes, and any structures on it that never change. And then the live load will typically refer to any loads applied to the structure, so a lighting boom, perhaps, heaven forbid, a piano, or an actor. Dead loads, live loads, static loads, dynamic loads. Okay, all of those are definitions that get us to being able to talk about one of the fundamental principles of safe structures on stage that we're going to need to understand to really think about pre-qualified structures and pre-engineered construction techniques, and that is equilibrium. Structures that don't move when forces are applied to them are said to be in a state of static equilibrium. Think about the post earlier. It doesn't move even though there's that 100-pound weight on top of it. When in static equilibrium, all forces acting upon a body or a structure produce no change in the motion of the structure. And that's good, because if we want a structure to stay in place, we don't want it to move anywhere, right? So static equilibrium technically means that the sum of all horizontal forces, left, right, front, back, or any angle in between, equals 0. The sum of all vertical forces, up and down, equals 0. And the sum of all moments about any point, so any place where there might be rotation, there is none, because all of the forces that could cause rotation equals 0. To be in equilibrium, any forces that act on an object or structure must be canceled in some way. Safe structures combine panels, beams, and columns of appropriate sizes and materials in ways that cause the stresses in these members to act in opposition to any outside forces. I'll say that again. To be in equilibrium, any forces that act on an object or structure must be canceled somehow. Safe structures are made up of elements, plywood sheets, 2x4 beams, and maybe Schedule 40 iron pipe legs or columns of appropriate sizes and materials that are combined to cause the stresses inside of each of those members to resist any outside forces. Pre-qualified structures and pre-engineered techniques use systems designed to resist very specific forces related to very specific loads. When used within those parameters, those very specific forces and those very specific loads, these structures are incredibly safe. When used beyond those parameters, their ability to withstand forces can no longer be predicted. So it's important for us to understand one last term here, loading capacities. Loading capacity refers to the largest combined live and dead load a structure can support safely. Typically, that's defined by some sort of federal, state, or local building code. For example, Indiana Building Code states rooms and houses must be designed to support a uniformly distributed load across the whole floor of 40 pounds per square foot. When designing platforms for the stage, we often plan for a combined dead and live load, a distributed load of 50 pounds per square foot. That accounts for the structure itself. That accounts for the fact that we're going to see some dynamic loads that may be bigger than what we see in a house. We don't often see 50 dancers in a kick line, for example, in our living rooms, but we will on platforms on stage, or we could anyway. So pre-qualified structures will indicate the loading capacity that they can support and the assembly requirements necessary to meet that capacity. To sum up for today, we've covered a lot. What's a pre-qualified structure or a pre-engineered construction technique? These are structures or techniques that have been defined by engineers in advance so that they can withstand specific loads and situations. And when followed and used correctly, they will live up to that promise. In order to understand how they work, we need to understand what a load is and a force. And a load is basically any weight on a structure, and a force is the result of that weight. It is some kind of a push or pull that could cause an object to move. A stress is basically an internal force that resists an external force. It's the reason why a Coke can doesn't crush right away when you step on it, because the stresses inside the Coke can are resisting that force. There are a couple of different kinds of stresses that we like to talk about. We're going to talk about axial stresses. So those are act along the axis of an object, and compressive stresses are axial stresses that resist crushing. Tensile stresses are axial stresses that resist pulling apart. Tangential stresses act across an axis. So shear stresses resist a tendency of an object to want to slide against itself, like a bolt in a joint wanting to sort of shear itself. Or torsional stresses, a resistance to forces that cause twisting. All that helps us understand the principle of equilibrium, which is that if all of the forces acting on an object from every direction are canceled out, it won't move. In order for that to happen, internal stresses have to be thought about such that we use the correct orientation and material choices of members to resist all of those outside forces. All of that is going to help us understand how pre-qualified structures and pre-engineered construction techniques work. Thank you.